So this is going to be your Fast and Furious review, especially for those of you that aren't in the review class. There's several concepts on here that we can go through. Start out with limits, and there are finite limits. This says try direct substitutions first. Very rarely does that work as getting a limit. So you're going to do some different things, either factor and reduce. You can multiply by the conjugate. An example of the conjugate would be if you had 5 over radical x plus 2, the conjugate of that would be radical x minus 2, and you're multiplying that by the numerator and denominator. When you multiply that out, you're going to simplify the denominator, but leave the numerator as is because something will cancel out. The last one is L'Hopital's rule, which basically if you plug in and you get 0 over 0, in other words, you can't find the limit, you can take the derivative of the numerator over the derivative of the denominator and then substitute in. If you still get 0 over 0, you keep doing it until you can substitute in, and that also works. Infinite limits, there's 3 cases. The first case is if the numerator is smaller than the denominator. So if you had x over x to the third plus something, that means your limit is going to be 0. That means that over time it's going to approach the x-axis. If the numerator is equal to the denominator, then you have a horizontal asymptote at the leading coefficients. So looking on here, see if there's one. So if this said this is to infinity, and the leading coefficient here is x to the third, and this is x to the third, you'd have a horizontal asymptote at y equals 8/3. The last case is if it's larger than the denominator, then the limit doesn't exist. It's going to be infinity one way or the other. Limits from a picture, almost always we're talking about some kind of a hole in the graph, some kind of piecewise function. Remember that the function value doesn't have to exist for the limit to exist. So like on this one, the limit is 1, 2, 3, because it's approaching 3 from both sides. The function value, however, is 1, and that connects you directly to the definition of continuity. If the limit is not the same as the function value, then obviously there's a space there. Another place you have an issue is if there's just no function value at all, then this case they're both approaching positive infinity. So a real limit doesn't exist. And one like this, the limit exists in pieces. So your limit from the left is 2, your limit from the right is 3. And so the limit does not exist. There is a point f of 2 that exists. Okay. So different types of continuity, we call this a jump. Removable discontinuity means if you had something you could factor out and cancel it out, that's a removable. It's a hole in the graph. And then you have just non-removable, usually with a piecewise function. And they show the different kinds of non-differentiability. That always connects because if something is differentiable, then it's continuous. If something is continuous, it's not necessarily differentiable. We look for cusps. So especially corners, vertical. So if you had to draw a vertical tangent line, any kind of thing right here, this is not continuous, so it definitely cannot be differentiable. The question that you will probably see has to do with piecewise functions. When you see a piecewise function and you see anything with continuous differentiable, they're always talking about the overlap. So if you plug in 2 to this function, you get 4 minus a. If you plug 2 into this function, you get 2b minus 8. And so they're going to ask about the relationship between those two. If they are the same, then wherever this function, this is some kind of parabola, wherever it leaves off, the other one picks up there and does its thing. It's a line, whatever, it's going this way or that way. It doesn't really matter. You just need to find out, is the value at 2 the same here as here? And this one, you could only get a relationship. Intermediate value theorem connects to initially your definition of the derivative. It's talking about the number of guaranteed solutions. And so you're looking at intervals. If it's continuous and differentiable, and you know f of 1 is 5, so we have that point. And f of 5 is -3, you know that you're guaranteed to have at least one solution if it's continuous. You might have more. It could go up and down, up and down, up and down, but you know you at least have one in that interval. Basic differentiation rules. These are ones that we memorized. We took a quiz on. Product rule, quotient rule, all these. Remember, all of the co's are negative. Any co is negative. Natural log is u prime over u is how we usually said. That's what the du is, but u prime over u. And always remember that when you take the derivative of e to the u, it's e to the u times u prime, du. Product rule, quotient rule, chain rule. One that we didn't talk about during the class, but we did during the review. If it says to find the derivative of an inverse, it's a little easier understood if it's f of x and g of x. They'll usually say g is the inverse of f. They'll say, what's the derivative? The derivative is 1 over f prime of g of x. So it's a reciprocal, sort of, a kind of reciprocal chain rule. That's one you can memorize if you want to as an additional property. There'll be maybe one question on that, so you have to weigh out whether it's worth it or not. If you want more information, you can look up derivative of inverses. Okay, rules from a table. So rules from a table, ignore the table, do the property, and then go back and plug these in. We did do quite a few of these. So do the product rule, f prime g plus g prime f, and then plug in 2, and then you can get your values from the table. The one that is most likely to be asked about is the chain rule. It's the derivative of the outside times the derivative of the inside. And don't forget that this is the chain rule notation. The wrong answer that includes not putting the g prime out there will definitely be on the answer key. Okay, equation of a tangent line. Always, 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 always. You know your point. Plug it in. Start writing. So when you know on this first one, you know you have a point. Don't even have to look at the question. You know you have this point. And then the derivative comes from, or the slope comes from the derivative. So you're going to find the slope, plug it in. If they only give you an x value, you can find the y value otherwise. They can ask questions. What value does this have a tangent with a slope of 6? In that case, you just need to take the derivative and set it equal to 6 and find out where that's at. If it says something about parallel, find the slope, set it equal to whatever that slope is. So these kind of connect to some algebra questions. Find the equation of the tangent line through the point 1 through 6. Use your local linear approximation. So linear approximation means find the tangent line and then plug in 1.1 for x as a way to estimate. Because tangent lines, if that's your tangent line, if you find something real, you can use that tangent line to approximate a really close value. So tangent approximation, big concept. And that's concepts 1 through 7 on this list.